During the first part of our lecture, we will take a closer look at mean and standard deviation as a measure of location as contrasted with a measure of scale. In the second part, we will draw attention to the basics of inferential statistics. In particular, we will speak about the notion of probability, random variable, probability mass function, probability density function, normal distribution, standard normal distribution, standardization, and standard normal table. First, let us recall what the terms sample and population mean. A population is a set of objects, persons, schools, hospitals, etc., for which an empirical study using a subset, a sample, is supposed to make a conclusion regarding certain characters. There must be an operational definition for the population that allows for an assertion of whether a certain object belongs to it or not. Moreover, the populations must be defined exactly with regards to space, time, and content. A subset of research units sample subjected to observation is obtained through sampling. In mathematical statistics, populations are often considered or modeled as infinitely large. This proves especially worthwhile if the size of the elements n is sufficiently large. Example, n is more than 1000. Rarely, there is a complete inventory ascertainment of the population, or in other words, a census of the population or universe. As with statistical almanacs, sample is a subset of individuals chosen from a population. In statistics, a data sample is a set of data collected and or selected from a statistical population by a defined procedure. Previously, we spoke about measures of location and measures of scale for values of a character. I will remind you that we measure location by finding a typical or central value that best describes the data. To measure scale means to characterize the spread or variability of a dataset. Variability is a quantitative measure of the differences between scores in a distribution. Variability describes the degree to which the scores are spread out or clustered together. The mean, as the most important measure of location, is calculated for quantitative characters. Its corresponding measure of scale, which here describes the variability of the outcomes, is the square root of variance, that is, the standard deviation. Here are the formulas to calculate an arithmetic mean of the values of discrete characters without taking frequencies into consideration. There are two different formulas for population mean and for sample mean. By using the sigma sign, we obtain the formulas given on this slide. Below the sigma sign, the current index is specified with its smallest value. Above the sigma sign, the largest value of index is specified. Although two formulas look completely different, the calculations is entirely equal in terms of concrete numerical values. This is not the case as concerns the variance. In the population, the variance is defined as the arithmetic mean of the squared differences of the individual outcomes from the mean. In a sample, the variance is defined as the sum of squared differences of individual outcomes from the mean divided by the number of observations having one subtracted from it. In both cases, standard deviations are defined as the square root from the variance. Here is the example of how these formulas can be applied. So we sum up values in the sample. We divide by the number of observations. And then apply the formula to count variance, and its square root gives the standard deviation. Here's another example of using a variance of a sample, of calculating variance of a sample. It can be seen from these figures how much the standard deviation contributes to the characteristics of the distribution of the outcomes. The standard deviation ascertains the extent of dispersion of the outcomes around the mean. Thus, a population can be described very accurately with two statistics, a measure of location and a measure of scale. Vice versa, it is also clear from these considerations that the description of a population using the mean alone is completely inadequate. A classic empirical example at the turn of the 19th to the 20th century shows that although an approximate average age of death was more or less the same for men and for women, the dispersion of age of death was much larger for women. It is a very relatively large number of women died very young, mainly as a result of childbirth fever, even though quite a lot of women also became very old, much older than men. If sampling by chance, that is random sampling, this is the best option in most cases. Previously, we spoke about random sampling as the most frequently used sampling method. Random sampling means to take elements from a population in such a way that each element has an equal probability of being chosen. In other words, each element has an equal chance of being sampled. The term probably has to be defined precisely in the following due to the fact that in everyday language, probable is often used quite differently, mostly in the sense of a relatively low uncertainty. For instance, it will probably rain today. Within the framework of probability theory, the probability P for any event E is defined as a real number between 0 and 1 with certain mathematical properties, most of them corresponding with those of relative frequencies, at least if a same if a sample is extensive enough. The higher the probability of the event, the more confident we can be that this event will occur. Correctly must be expressed as follows. There is an event which is most likely to happen. So this event has a probability near 1. In contrast, events which are unlikely to happen have a probability near 0. In statistics, the probability of an event is interpreted as a relative frequency of the occurrence of this event in a long run of observations under equal conditions. In case the event E does not occur, we denote it as event E dash and say that the event E and E dash are complementary. A certain and an impossible event have probabilities of 1 and 0 respectively. In many cases, a probability statement of a particular event refers to several options of realization or measurement values, all having the same probability of occurring and all coinciding with this particular event. We denote the number of all realization options by E and the number of those which coincide with the event E by G. Then we have the following formula which we can use to count probability. For instance, the event an odd outcome in throwing a die occurs for the 3 equally likely outcomes out of 6 possible outcomes. As a result, we get the probability of 0.5 that we get an odd number throwing a die. Let us take a look at the example. In a survey, 211 women and 198 men are asked about their attitudes towards psychotherapy. When you have personal problems, do you visit a psychotherapist? The result of the survey is as follows. Using the absolute frequencies given in this table, we can now count the probability of a positive attitude, the probability of a negative attitude, the probability of receiving a response from a woman, and the response from a man. If we are interested in defining the probability of an event A, if the event B has already occurred or vice versa, we have to define the conditional probability, which is denoted as follows. In our example, we now consider a question. What is the relative frequency of the positive attitude for women And count the conditional probability by dividing the number of women who answered positively by the total number of women.